survey data rates. Disk drive storage has been under quite a lot of pressure recently, but there's a lot of signs telling us that this will catch up again. So disk drive storage has been doubling every 23 months, way quicker than the SDSS to LSST trend. The big worry is that I/O bus speed in various reincarnations isn't keeping up. So it is true that the I/O, the number of the capability of your computer to steal bits around within your system, isn't at all keeping up with Moore's law in terms of transistor count. So this is speeding up doubling every 35 months, which is slow. It's a problem. It makes people say that we need to move data to computing rather than moving the computing to the data. But that's actually not true, because our big surveys are still evolving slower than this. Right? So things are getting better on all these fronts. And so the big point I just wanted to make with my rant is that if these trends continue for another little while, and it is decidedly not true that they can continue forever, because we'll end up with processors that have more transistors than there are molecules in the universe otherwise. But if the trends continue for another little while, we have this amazing increase in computing power compared to the pixels. And the point I want to make is that in CCD astronomy, there is no data deluge, there's a deluge of computing power. Right? So when you develop packages, you might want to keep this big picture in mind. Decidedly not true for radio astronomy, which I know far less about. So let's all ride the wave of computing power and be critical when people scare you with the data deluge and so on, because it's computing that's being evolving really quickly, and it's exciting.
Okay, David, sir. No questions in line in talks, I'm afraid. You have to do the next level. Question for you in the village. David here?
David's coming.
Oh, yeah. Okay, so the next speaker after David is Matt. Okay, so where are you?
Over here.
Oh, hi Matt, so you can come up when the alarm goes off, okay? Yeah. You got a... This goes in. So we'll help with the connections. I'm not sure. The connectors and Mac laptop. Is that a window call?
No, that's the Lenovo one, I think.
Sorry?
That's, I think it's her laptop.
That's good for you?
I'm David Saroff. I'm working with Duncan Lorimer of West Virginia University and Stephanie Baum and Chris O'Day of the University of Manitoba. I'm a graduate student, although I'm old enough to be two graduate students. My project, we're using this telescope. This is a football field across 100 meters. We believe it's the largest moving structure on Earth. It's the second largest radio telescope. Arecibo is the first. And I'm looking at the Andromeda galaxy for pulsars. This is some children coming to visit. There's the telescope again, and it's almost a mile beyond them. This is just to show where we are. This is Andromeda. This is us. This is the local group. so far there have been about 2,000 pulsars detected in our own galaxy, and a few in some of the dwarf galaxies nearer to ours. And you notice that they center on the side where we are, because we're trying to look through the disk of the galaxy. And that of course obscures things. But the point is, if Andromeda is like the Milky Way, then we expect there to be about 10,000 pulsars. And I'm going to say in a second, there are about 1% of the pulsars, along with the tick, 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 steady pulse, occasionally give off a giant pulse that might be 1,000 or 10,000 times as big. I have no chance at all at seeing the regular tick, tick, tick of pulsars in Andromeda. We're too far away. But I'm looking for the giant pulses. So this is the supernova that exploded about 1,000 years ago. That was recorded by the Chinese court astronomers. It's the crab. And this is the usual tick, 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 tick of the pulsar. And you see that it emits all the way from the radio up into 100 keV photons, even higher. This is an old graph. But it's these occasional very large pulses that if a crab-like pulsar is in Andromeda, I have a chance of seeing from Green Bank. Studying the crab pulsar, just like hurricanes, very large hurricanes are rare. Very large earthquakes are rare. Smaller things are much more common. So this in astronomy is a power law that is the signal to noise, which gives an idea of the size of the pulse and how frequently it occurs. And this is the curve for the crab pulsar. So I'm only going to be sensitive to the very tail of this thing. Otherwise, my signal is all in the noise. We had very odd coordinates for the pointings. We followed a paper that claimed to see pulses from Andromeda. But it was done with the Westerbork telescope, which is a linear array. And for a linear array, then you get this washboard pattern of where the source might have been on the field of view of the telescope. And it's only if you can see things multiple times as the Earth turns that you get some...
I'm afraid. Sorry.
Oh well. I didn't even get to the point of the talk. It was just all introduction.
That's okay, we'll have a great talk over lunch about it. Thank you. Okay, so read next plant and then Becky after that.
Thank you.
So there was a dongle up here 15 minutes ago?
I know.
All free.
Is there any of them right? Do you have a back dongle?
There's a bucket of them.
Yeah, it's not
Yeah,
in
it's
here.
not in the bucket.
It's not in here.
How'd you run the break?
Here we go. Here we go.
Here's what we're right now.
Oh, it's
That
the
was
same
good
one.
work,
Yeah,
But
sorry.
it's black.
By the way,
It's black. It's not a
I would like to take this opportunity to let everyone know you should put stickers and like write your name on a permanent marker on all your Mac accessories, on your power cables, on your dongles. Stickers and label them. Return address labels work well. Yes. If you want ever to see your dongle again.
I want that dongle back.
But I just put my initials on it. All right, I want to spend a few minutes showing what you can do with basic IPython widgets, and follow that up with an offer to do an unconference session on that later this afternoon. So I'm going to skip over the beginning parts of this notebook where I'm doing imports, reading in some data. This is a homework assignment that I gave this week while I'm gone. It's due later today. And so see how the students do with it.
How quick you can get the video up on YouTube,
Students contribute to SunPy. Stuart's about to do you a favor. So let me make this plot real quick. So this is a plot of type 1 supernova data, pretty standard plot, distance on the horizontal axis, velocity on the vertical axis, overlaid with a line showing the Hubble relationship. If you take that block of code that's just a bunch of standard plot statements, wrap it up in a function, and don't make the default value the right one. And then wrap that function in all the widgets interactive, and you get this. And so just to be totally clear, the idea of this is not to do real fitting on Hubble constants. It's an idea. Just trying to make it totally clear. I don't know much of statistics, but I know enough to know that. But the idea is that you can visually get pretty close to the right value, and you don't get lost in details of the math. What's really handy, I should maybe mention, I should have pointed one thing out in the imports, right? There's Astronomy all over the place. So this part would be fairly straightforward to do with other packages, maybe. What I'd like them to do, because this claim that there's 95 or so % of the universe we can't see is a fairly extraordinary claim, is allow them to put in the value that they got from the Hubble constant up above. So that's what, 65, I came out low, but. And update the plot with the Hubble constant. And whoops. Then as you drag the sliders, in the background what's happening is that Astronomy cosmology is being used to reconfigure the model and overlay the plot. You may notice that if omega is 0.48, say, and it's flat, omega energy is not actually 0. The upside of widgets interactive is it's very easy to use. The downside is that it's not very flexible. So if I wanted to write my own widget, and I'll show an example of that tomorrow morning, it's not so hard to couple those together. But I was rushing to get this online before the conference started. So, so you can play with flat models, non-flat models, and then you can ask them a bunch of questions about, okay, what changes when you change this parameter, and why does it change that way? Give you a physical explanation of why it changes that way. And this sort of thing was impossible to do when or it would have been very difficult to do 2 years ago when I taught this course. Putting this together took very little time. So I'm actually going to finish before the buzzer goes off with this. If you want to play around with widgets, but I still got a minute, right?
Yeah, you still have a
Good, then I've got time for the 2-3 joke. So if Python 2 and Python 3 wasn't confusing enough, there's now IPython 2 and IPython 3, and IPython 3 widgets have changed some, and so I know about these. I won't know about those till class is in a week. But I'm happy to do an unconference session if you want one right downtown that works for you and come with an idea of a draft you want to make.
Okay, next after Becky, we have Carolin. So, ready?
Alright, hi everyone. So I'm going to talk to you about StarPy, which is something that I've worked on in my PhD studies. Basically, if you've ever wanted to work with stellar population synthesis models, things like Bourgeois and Charlot, or Marston models, for anyone who's familiar with it, they let you basically take an IMF and say, okay, if I have this population of stars that's distributed this way, then how much flux am I getting out at all the different wavelengths, and what is a model SED? But if you actually go to websites and you download the raw files they give you, they're really ugly and they look like this, and it's really hard to extract all the information because they're given at all these different ages and wavelengths and different combinations of different IMFs, and you're just panicking, going, oh my god, what am I even going to get out of it? So I started off by, first of all, okay, I want to work with this, so I got to extract that. So I wrote a code to extract Marston 05 models and extract Bourgeois and Charlot models really easily. And then I thought, okay, what I'd really like to do is to say, okay, this basically just gives it you for a really simple cell population that you start off with like a solar mass and it just sort of evolves over time. What I'd like to do is say, okay, for a galaxy, I'm going to model its star formation history, or for a star cluster, I'm going to model its star formation history. Maybe something really simple with two parameters that you describe your star formation history with. You say maybe like a time that the star formation history decides to decline, and then a rate that it declines at. And before that, it was just constant. What I want to be able to do is take those cell population synthesis models and say, okay, at every time step that I give it, calculate how much more mass I've made, and then calculate how much more flux that I get at each of those time steps, which is really useful. Integrate all that together, and you get like a model SED out, like the black line. I can put filters on it, SDSS filters, UV filters on it, infrared filters, and I can get photometry out from my model. My really basic star formation history model. Because online, what they give you is basically just these kind of like GUIs online that you can basically just sort of get very simple stellar populations out when actually you want more complex star formation histories. And you can put in any you want to describe. The really useful thing is, okay, you could try one combination of those parameters, like time and the rate starts to decline and rate that it declines at. But you want to know which one's the best one to describe an observed galaxy that you have, or an observed star cluster that has specific photometry. And so what you do is, I wrote this program called StarPy that lets you do all this, but it also lets you run it through MC, Dan Foreman-Mackey's great MC hammer code, and helps you figure out what actually is the best of those star formation histories that you've given it to describe your observed photometry, which is really cool. And I had a paper from this, and I think it's really cool that you can actually do this now, because I don't think this existed, and now it exists in Python at least, and it's all on GitHub. Zooniverse.start.by. Which is really cool. The other thing I wanted to say while I'm up here, because the buzzer hasn't gone off yet, which is awesome, is that Astronomy is going on despite the fact that Rob Simpson, our sort of leader, chief, has left us. It's only ever been in the US and Europe before, but this year we're actually bringing it to Australia for the first time. I should say that Astronomy is basically it's an international community of researchers, developers, educators, communicators who all believe that we should have really cool web tools to do amazing things with. So we work a lot in Python, we work in JavaScript, and we like to get together, we like to hack, we like to unconference, we have keynote speakers like this, and I think this kind of crowd would really enjoy this conference, and you should really think about applying when applications open, I think, for the Sydney one soon, around about May. That's going to be run by Amanda Bauer in Sydney, and also we have Vanessa as well as on the LOC for that. And then I'll be heading up one in Oxford in June next year as well. So please all think about coming along, because it'll be great fun.
to. But I'm going to have a happy one with a happy ending. So I'm going to talk about teaching at university. So I'm mostly a Python user, and I turned into a Python educator last fall. When two people came up to me with this face people have if they want something for you, but they're smiling at you very nicely. And they said that, so we thought that the students should really learn Python, but we don't actually know Python. So would you do that for us? And I said, all right. If I'm the best one you have, I think I'm a bit scared, but good. So I asked him, so what would you like me to teach the students? And this is the list I got. So they were saying, like, teach them all the data types, teach them reading files, working with arrays, if statements, loops, functions, plotting, fitting, and some statistics. And I said, well, so how many weeks do I have? They said, well, you have 2 hours, and you should teach them some science, and you should also have them do exercise. And this one, they started panicking. So I went to the astronomy group on Facebook and asked, has anyone done this, and how did you do that? And so they gave me some tips, and I got this wonderful notebook, which I made a bit simpler. And then I thought I'd practice it on the best I got as a sample for, like as an example, undergraduate student, which is professors, postdocs, and PhD students. And I tried to teach them all of that in 2 hours, and in 3 hours I got through a quarter of it. So I realized, okay, this was not going to work at all, which was about 3 days before the tutorial was supposed to start. So I went down to this. So what I did in 2 hours was, I made some example code. I opened the Python shell, I typed something for them, and I said, look, this is an array, this is how you use it. I gave them an example sheet, and then I let them loose on a bunch of data, and told them to play with it. And they did quite well. I had wonderful demonstrators which helped a lot. In 2 hours, they did things like this. They had a function that calculates a black hole mass from data, and in 2 hours, all of them got to this, which is that they had calculated themselves and they had fit a line to it. And they were still alive. In 2 hours, I think I was quite proud of them. And they were also breathing and, not completely shell-shocked. So I'm not saying that this is the ideal way to teach Python, but I think one thing this shows is that in a few hours you can at least show students, look, this is something useful you can do with the programming language. So you don't have the thing which you have a lot at universities, which is students get some introduction to programming, then they don't use it for about 4 years, and then they come to computational astrophysics and have to use Fortran and basically want to kill themselves. And I think that that's not the right thing to do it. And the other thing is also that people seem to like Python. Even the people that don't use Python seem to think that Python is a good thing. So I think we can easily raise hell and get something good to happen. And that's my hopeful rant. That's all.
Sorry, what was the name of the course or the workshop, or what did you call it?
I don't know how it was called in the end. I think it was called, I had to call it.
No, but like, did you get some of this from some other place, or did you come up with all of this?
That worksheet I came up with all by myself.
Okay, cool.
It's based on public data. I can give that to you if you want.
Yeah.
Could you tweet it, please?
I don't tweet.
Send it to the email list, to the email list.
I'd have to put it somewhere first. And I can do that.
Thanks.
They'll just give you them a second.
Okay, perfect. Thank you.
Hi everyone. So I would just like quickly to show you this because it was raised in the stats sessions we had a couple of days ago. So experience tells me that it's important to begin telling what this is not, right? So this is ABC is approximate Bayesian computation, and it is not a replacement for MCMC. If you have a likelihood and you're pretty happy with that and you're able to calculate it, do an MCMC, right? This is only when your likelihood is too complicated or too time-consuming that it's not feasible to integrate it all the time you want to do to do inference. And other thing is, you need to have a simulator, and this is not a test for your simulator. You should trust your simulator before getting into this. So basically, the point is, if you suppose that I have an observation, I measured temperature at somewhere a lot of times. So I will have
this is my data, right? I will have a Gaussian. Maybe this is the temperature and the times. I measured it many times. I have that. I have a simulator which produces a lot of catalogs. So this is a catalog, and I have a simulator that produces a lots of catalogs depending on parameter input. So in order to make it easy, suppose that I can. The only thing that I need here is the mean, right? So my simulator does is it generates a lot of different catalogs. I use the distances between the simulated and the real catalog in order to say, okay, the parameter if this is close to this, the parameter that I use to generate this simulation is probably close to the true one. That's basically the idea. So what this does, the Cosmo only comes because the package is coupled with a library who do cosmological simulations. But the simulator, the input, the distance function everything is input, so you can plug into your own simulator and use it to your own problem. So in this simple problem that I show you, the results would be something like this. So it does that for a lot of iterations, and you see that you start in a second. Okay, so you start with your priors, which are pretty big. I cannot stop this. So you start with your priors, which are pretty big, and over the iterations, it goes evolving and learning the correct posterior probability distribution over your parameters. So I hope the paper accompanying this, it was done using galaxy cluster number counts, cosmological inference from galaxy cluster number counts. I hope it's going to be online very, very soon. For example, tomorrow. So in my talk tomorrow, I hope I can show you the galaxy cluster things and a plot where I can stop so we can see all the snapshots quickly.
Thank you.
Instead of giving me a variant 4 minutes, if you give me one at 1, because I have 4 minute video, go up 3.5 minute video to show.
1 at 1.
Thanks. Good to see how fast. Okay, so I'm just going to give a really quick demo of some software that I've been working on that I call Toyz and Toyz. So it's for data analysis and visualization. So just to give you a quick idea of what it is, it's basically a web framework that sits on a server. You can, let's see, so to access it you just need to have a client on a web browser. So this is really good for something like a classroom where you don't want to have everybody install IRAF on their computers, but you'll still be able to do photometry and object detection and astrometry and everything right from a browser. All of the GUIs are made from Python dictionary, so it's really customizable. You can kind of think of this as like a front end for AstroPy. So if you have like any tools that you use over and over and over again, and there's you can envision a quick way with buttons or drop-down menus, this would be a good place to do it. The GUI, I have a parser that just takes a Python dictionary and then it converts that and does all the JavaScript and HTML for you. So it has support for multiple users, so that each user account has their own directories. They can only view files in their directories. Okay, so the goal is so that an undergraduate student can start analyzing data on their first day. So now I'm going to really start talking fast as I show a video here. Okay, so to run it, you just run Toyz from the command line, and so then you open a connection in the browser. It has an admin console, and this is where you can set all the user settings, user directories, and which Python modules they have access to. And then the main entity in this is a workspace. So essentially you can create tiles, and these tiles act kind of like widgets or other things. So they're running, so this is all happening in the browser, but all the processing is done on the server. So one of the widgets, the default widgets, is an Astro viewer. So you can view FITS images, PNGs, anything that the Python imaging library can open. And you can view it as a large image, right? So I can take a 30,000 by 30,000 pixel image
but I only send the parts that are actually being viewed to the browser. So I make JPEG tiles that get sent to the browser. So you can do color maps. The color map, I have a separate window just because this processing's being done in the browser. So you can choose any Matplotlib color map, modify it on here, and then you tell it to set it on the server. It sends that data to the browser. You can scroll, just using touch scrolling, so you can actually do this on a tablet. You can, if you have images, you can click on them and get like surface plots. It fits all the points. You can choose which type of fit you want to use. So you can do the histogram. So this is kind of IM exam. So you can get histograms for background. You can choose what size window you want to look at, and it calculates the statistics for you. I haven't quite finished this part yet, but it'll be able to do object detection and build a catalog. And then once you have a catalog, you can click on sources and add new sources. I don't know if you can see the blue there, but it's making circles where all of the where it's detecting outlish, and then you'll be able to click on them and delete them if they're bad sources. Let's see, and then it's really easy to be able to switch between frames. So this one has 9 frames, and so you can just get a drop-down box and go to frames. And it'll keep the same color map that you had, on the other frames in the image, so you don't have to keep redoing it each time you switch frames. It's taken a while to load here because my computer couldn't really process doing the video and doing all this processing at once. So the other parts of this is kind of like glue, except this is all data that's on a server. So now you can link to a data source. You can use any kind of module. So let's say we use Astronomy. You can choose any kind of file type. You can choose any kind of format for that file type. It also uses pandas, NumPy, or you can make your own very easily. And then just to save time, instead of loading all this myself, I saved a workspace. So now I can load it again. It has all the plots that I made on there. And then if you click a point, notice that they're all connected to the same data source, so it selects that point in each plot. So it's a good way to be able to look at high-dimensional data. You can select a lot of points. You can remove them. It removes them from the server, as well as locally. And in a second here, I don't know what I'm doing for this part of the demo. I'll show you how it's really easy to add new. So I can actually add onto this plot by just saying I want to set a new series. I select the data source I want to use. I have a drop-down box that shows me all the columns, so I can choose my X column, my Y column, set it. Now you see it generated an extra plot on there. I know that was a lot to throw at you real quick, but that's just what I want to show you.
Alright, so I just want to tell you a little bit about cosmic ray rejection and some of the code that I've implemented to do that. So, the cosmic rays are a big pain in the neck for optical astronomers. If anybody's ever dealt with raw HST data, you know exactly what I'm talking about. And so this is what you get when you get an HST data. You have kind of a rather mundane galaxy sitting in the center, but you have all these other cosmic rays. Now most of these, basically all of the things besides the galaxy you see here are not real. There's maybe 1 or 2 stars. And it turns out if you're doing image registration and things like that, computers aren't necessarily good at distinguishing which objects they should match. So you can see that there's a lot of these cosmic rays in HST images, something like 1 to a couple % of the pixels, depending on how long your exposure were, are affected by cosmic rays. So how do we deal with that? Well, there's a variety of ways. So this is my talk, so I get to talk about my code. So this is an implementation of something like the Lacosmic algorithm. It uses the Laplacian filter to try and pick up edges of a subsampled image, and then it rebends it to detect cosmic rays. basically the idea is that cosmic rays have sharp edges, stars do not. And so that's how it uses to distinguish it. And so when you run the code, this is what you get originally, and that's the cleaned up image using the algorithm. So it seems to be doing pretty well. There's a lot of subtleties in there, and I would love to talk to any of you about them if you like. But in the meantime, so some of the differences, this has been around for quite a while. Now, when I ran the original Lacosmic, which was implemented in IRAF, it took 5 minutes and 10 seconds per chip, per frame. And so it would take 10 minutes for one ACS image to do that, to run Lacosmic on it. Toyz has a nice version that he ported over to Python that's a little bit better, something like 1:37. Through a lot of different techniques, I've got it down to 3.5 seconds. And so that's 28 times faster than the Python version and 90 times faster than IRAF. So how do we do that? There's a lot of ways. One of the big problems with the IRAF version is that it writes every step to disk, and so that's kind of a problem. The other thing is you want to calculate the median in a smarter way, so using using faster techniques, so using the right search algorithms. So a lot of thanks to Nicholas Devlard, who developed a lot of these median techniques 15 years ago for ESO. He now does security on Android, so he's probably still helping us in ways we don't even know. The other major difference is I use a separable median filter, and so you can cut down, you get another kind of n-squared performance increase there. And then I used a lot of C and a lot of Python to wrap this and then put it into a Python wrapper. So here's some of the median algorithms. So some of these I hope will be useful for other applications. So if you have specialized median questions, we can put this in maybe into an AstroPy, like a median utils type package or something. But right now it's just in this Lacosmic X thing. So yeah, that's basically all I wanted to say. There's a lot of customization I've added to it as well, and so it was kind of inspired by the original Lacosmic algorithm, but I've made a lot of changes. So how you remove some of the stars from the image so you don't detect them instead of cosmic rays is quite a bit different. And so there's a whole bunch of different parameters you can use depending on what type of data you have. So if you have questions and want to learn how to use this, I'd love to sit down and talk with you. I've also, Edward pointed out it might be useful to come up with a better name, so if somebody's got a better name idea, I'm also open to that as well. So otherwise, well, yeah, that's it. So let's talk about this. Thanks.
So I like the challenge of giving a lightning talk, so instead I'm going to give 2 lightning talks in one, within 5 minutes. So the first is I want to talk about a survey that I did recently of scientific Python users. And so the idea behind this was to basically just send out a Google form which included a lot of questions that were related to kind of what Python installations people are using and what kind of versions of Python. I'll explain in a minute. And we had 781 responses, included 434 from Astronomy, so there's actually a reasonably big data set. And this contains a lot of information about operating systems, Python, NumPy, SciPy, McCully versions, how people install Python, what packages they use, also how many years of experience they have, why they don't use Python 3, they don't use it, and also how they found out about the survey, which is also instructive, Twitter, Facebook, Google Wave, things like that. So basically, the idea is that I'm just going to show you a very brief overview of some of the data, and then if people want to hack on the data today or tomorrow, then I can make it available to you. So this is an example. Many people use Python 2.7. Actually, the second biggest Python version is Python 3.4, and then actually the other ones are almost negligible. So this kind of information is very interesting for when you're developing a package to know which Python versions to support. Based on this, I think we can pretty soon drop support for Python 2.6, for example. NumPy versions, so this is another example. A few people are using very old versions, but most people are using the two most recent versions. You can also make 2D plots. So this is an example. Now in these, the rows are normalized, so basically because otherwise there's fewer Windows users, and so we wouldn't see that. What this shows is actually that if you look at Python version, for example 2.7, 3.4, Windows users are actually the most up-to-date and have the biggest fraction of Python 3.4 users. We have other interesting information, like for example, correlation between Python version and NumPy version, which is also useful for when you want to test packages. This is another interesting graph. The SciPy version and the NumPy version correlate pretty nicely. And so again, we know that there's certain versions we don't need to care about supporting combinations of versions. Why people don't use Python 3? Actually, the biggest reason is that they have no incentive. So this is something to think about. More than half of people who don't use Python 3 say, why should they? So we need to think about how to solve that. So if you want to hack on the data, then please come and talk to me this afternoon. The other thing that I want to advertise is very briefly, so I'm the lead developer of ApplePie at the moment, and also a package called WCS Axes. I just want to have maybe a little discussion to clarify what the difference is. ApplePie is a package that was developed a few years ago, actually back in 2009. And the idea is to basically make it easy to make publication quality plots of images in Python. And it's a very high-level package. You can do it kind of tries to hide away a lot of the convenience. But many users actually want something which is close to matplotlib, which is where WCS Axis comes in. And so what this is it's simply a framework just to show to be able to show coordinate labels and axes and the coordinate grid on top of the image. But it's actually a lot more flexible than ApplePie, and so if you want to be able to customize your plot, this is a good framework. It works with SunPy coordinates, for example, once it's actually merged in SunPy. And so we try to make it very general so that it works with basically arbitrary coordinate systems. You can also do fancy things like custom frames, things like this, which means you can then do this, but it's actually this was actually made with WCS Axis. And if you're interested in using this, then please go to this URL. But what I would like to advertise is an unconference session to basically talk about how we go forward, how do we keep, essentially, one package is a more advanced package which allows you to customize things more, the other one is a kind of easier to use, a high-level package. So we should talk about this if anyone's interested. Thanks.
Thank you to all the speakers for keeping the time perfectly. We're actually early, I think, for lunch. So let's give everyone a round of applause who spoke in the session. Stuart and everyone.